So the question arises, when do I use the horizontal approximating rectangle where we have delta y, in other words, the differential dy, and the functions are given to us as a function of y? And when do I use the vertical approximating rectangle where the width is delta x, so the differential is dy, and the functions are given to us in terms of a function of x? Well, let's see. In the horizontal case, it's x right minus x left for the length and delta y for the width. But for the vertical approximating rectangle, it's delta x for the width and y upper minus y lower for the height, the length of the rectangle. But when do we do it? Here we're asked to find the area between x equals y squared and x equals y plus 2. So my first inclination would be, well, they gave these two functions to me as a function of y. So why don't I use the horizontal approximation where I can take the rightmost function minus the leftmost function, and I use a differential dy, and I use limits of integration y equals the lower limit c to the upper limit d. I mean, that is the one that seems most obvious because of the way the functions were given to me. But the fact of the matter is that it doesn't matter which one you use, whether you use the horizontal or the vertical. I mean, one might be easier than the other, but you should be getting the same answer. So first I want to notice that when they give us x equals y squared, it could be written as y equals plus or minus the square root of x. In other words, we could solve it for y. And when they give us x equals y plus 2, we could solve that for y and get y equals x minus 2. So we could always change the way the function looks by just solving for one of the variables. Step 1, let's find the points of intersection. Let's set x's equal to each other. We'll use the original form, set the x's equal to each other, and solve for the y's, and then we'll find the x partners of each of those points of intersection. The first x coordinate is equal to y squared, and the second one's given as y plus 2. That's given information. Solve for y. It's a second degree equation factor. Okay, so that gives us the solutions y equals 2 and y equals negative 1. Now we want to find the x partner by using either of the two given functions. The easiest one to use would be x equals y plus 2 to find the x partners. So when y is equal to 2, we plug it into the equation and it gives us x equals 4. When y is equal to negative 1, we plug it into the equation, it gives us x equals 1. So there are two ordered pair of points of intersection. Step 2, let's do a sketch this time instead of doing a table. We'll do a sketch. We're going to do two sketches. Here's my x and y coordinate. Here's my other x and y coordinate. The graphs will look the same. Okay, but we're going to call this one 1 and this one 2 because 1 will use a horizontal approximating rectangle, 2 will use the vertical. So here's my first graph and here's my second graph. Okay, now points of intersection are the same. They're xy ordered pairs. It's 2 points. And this is a point 1, negative 1 in both cases. And up there we have the point 4, 2 in both cases. Okay. Now here's my horizontal rectangle, my approximating rectangle. Okay. And this function on the left, x sub l, is y squared. The function on the right, x sub r, is y plus 2, just as they gave it to us. And the width of the rectangle is delta y, so we'll be using the differential dy. Okay, here's our vertical rectangle. The problem here is we have to divide this region into two regions because on one region there's something happening and on the right region there's something else happening. So we've got the y equals the square root of x on top of the first region and the y equals negative square root of x on the bottom of the first region, and then on the bottom of the second region we have y minus equals x minus 2. So we've got area 1 and area 2. We had to break it up because we have two different approximating rectangles. In the first region, the approximating rectangle, it has the lower function negative square root of x and the upper function square root of x. But in the second region, a sub 2, the rectangle has the lower function y equals x minus 2 and the upper function y equals the square root of 2. They both have delta x for the width. Now, see, we needed to bust up the integrals. The one goes from 0, you see how, and when I say 0, it's x equals 0, that's where the function starts, the area starts, and it goes to x equals 1, that first point of intersection, and then it changes from x equals 1 to 4, where we have a different lower function. We have a different lower function. Okay, back to part 1 or part I. We may do just one integral there from y equals -1 to 2 with x right and x left functions. But here for the first integral, for the a sub 1, we have the y upper equals square root, y lower equals negative square root. But then in the second integral, in that region, we have y upper is the square root, but y lower is the x minus 2 function. So we had to do this. We got it. We had to bust it up into two regions. Obviously, it would be easier to do the left side, but we're trying to show you how you could do it either way and still get the same answer. One's easier, one's harder. Okay, it's a long problem. It's a little bit too long for one video, so we're going to go on to the next video to finish it up.